In this video, we will see properties of cyclic groups. The first property is a cyclic group is abelian. Now we will consider G to be the given cyclic group generated by an element, say A in G. So what is meant by cyclic group? G generate. This is the notation that is used to denote a cyclic group generated by A. So any element in G will be of the form A par M, A par N, A par L, and so on. So here we consider X and Y to be any two elements in G. So by the definition of cyclic group, X can be written as A raised to M and Y is say some A raised to N. So where M and N are two integers. Now to show that G is abelian, we have to show that for X and Y in G, X dot Y is same as Y dot X. So we consider X into Y, replace X by A par M, Y by A par N. Then by index law you have this, and rewriting M plus N as N plus M commutativity in the case of integers is true, so you have this step. And again rewriting this as A par N into A par M, we have this being Y and this being X. You have X into Y to be equal to Y into X, and therefore your G is abelian. Next we prove that a subgroup of a cyclic group is cyclic. So you consider G to be the given cyclic group generated by A and G, and let H be a subgroup of G. Now if H is just singleton E, then H is generated by E. So we shall assume that H is different from singleton E. Now to show that H is cyclic, we must produce a generator for H. Now since G is cyclic, every element in G is a power of A. And now let M be the smallest positive integer such that A par M belongs to H. This is possible, that's by well ordering principle. Now what we are going to claim is this A par M is the generator for H. That is, every H in H is a power of A par M. Now since H is in capital H, okay, we have considered this. So since H is in H and H is contained in G, H can be written as integral power of A. So H is A par N for some integer N. Now having got two integers, this M is there and this N is there. So having got these two integers, we can find two more integers Q and R. By Euclidean algorithm, we can write this N as MQ plus R with 0 less than or equal to R less than M. Now our aim is to have this R to be 0. So only then we have this H, which is A par N, and that can be rewritten as A par MQ, so that you can have A par M power Q. So that your capital H is generated by A par M we can have. Now on the contrary, suppose we assume that the result holds for 0 less than R less than M. Finally we are going to conclude that this cannot be true, so we should have R to be 0 only. Now we consider A raised to N, that is A raised to MQ plus R, and that is rewritten in this way. Now retaining your H, and that is this is H, that is how we have assumed. So you have H to be this. Now retaining A par R, taking the rest to the other side, and that is pre-multiplying both sides by A par M par minus Q. This is what we get. Now already A par M is in H, so you have this also to be in H, and hence the product will also be in H because already small h is in capital H. So we have this to be in H, this to be in H, and therefore A raised to R should be there in H. Now we have this R to be less than M with A par R belonging to H. But we have already said that A par M is the smallest positive integer, so that A raised to M is in H. So we get a contradiction, and therefore we cannot have this to be true. There are two cases. One is R is 0, the other one is 0 less than R less than M. So we have ruled out this possibility, and therefore we must have N to be QM. So if we consider H, which was assumed to be A par N, and now that N is nothing but MQ, that is rewritten in this way, A par M par Q. So any H is written as some integral power of A par M, and therefore Capital H is generated by A power m. So A power m generate H, so H is cyclic. Now the next property is order of a cyclic group is equal to order of its generator. Now let the order of generator A of a cyclic group be n. Then we know that by the definition order of element, the definition of order of element says that n is the least positive integer for which a raised to n is the identity element. N is the least positive integer for which you have n to be the least positive integer for which a raised to n is the identity element. So that means you cannot have any s less than n for which a power s is e. You cannot have for s less than n a power s is equal to e. So a power s is not equal to e for 0 less than s less than n. So that is the meaning of saying that n is least. Now if we consider our G, which being cyclic, and A is in G, we must have A square and so on, A power n, which is nothing but E, all to be present in G. Now we claim that the elements in the above list are distinct. So suppose there exist integers r, there is a repetition, say r and s with 0 less than s less than r less than n, such that there is a repetition. Then we have a raised to r minus s to be the identity element, because you have assumed this. So from here you get this step, and obviously your r minus s is positive. R minus s is positive. So 0 less than r minus s less than n we get. So that's a contradiction to statement P, which says that for no integer less than n, you can have this to be equal to identity element. But we are getting that here. So that's a contradiction to statement P. Why that contradiction arose? Because we assumed that there are repetitions in this. So that proves that the elements in the above list are distinct. Now we have to show that the order of our ultimate aim is to show that order of a cyclic group is equal to order of its generator. So we consider G to be an arbitrary element in capital G, and we can write G to be a raised to s as G is a cyclic group. We have our a square, a cube and so on, a power n, which is e, to be the only elements in G. So we are going to claim that these are the only elements. We know pretty well these are all in G and they are all distinct. But we are going to show that other than these elements, you cannot have any element in G. So suppose for s greater than n, you have your a power s belonging to G you have, and that G you have taken as a power s. I have to show that G can be only one among this and not other than this. That is, your s cannot be greater than n. Right. Now we apply Euclidean algorithm too. So whenever two integers you're having in your hand, then you can go for your Euclidean algorithm. So we are going to apply Euclidean algorithm to these two integers s and n. So we can find integers q and r such that s is equal to nq plus r with 0 less than or equal to r less than n. Now we consider a raised to s, and that gives you this, and this is what you have after rewriting. And a power n is e. A power n is e, so you have this to be e, and so you have a power s to be equal to e into a power r. So that is just a power r with 0 less than or equal to r less than n. So if s is greater than n, then G, so what is that you have? You have shown that this a power s is a power r, where r is less than n. So it cannot be any element outside this list. So these are the only elements present in G. Hence a square and so on, these are the only elements in G. So what we have concluded, the our aim actually is order of a cyclic group is equal to order of its generator. First we assumed A to be generator, and we have said that n being the order, you have A power n to be E, and we have listed out the elements in G, and these could be the only elements present in G. So what does it say? It says that order of G is n. So it says that order of G is n. But order of G equal to n, and that n is nothing but order of A. So conclusion is order of cyclic group is equal to order of its generator. Order of the cyclic group is order of its generator. Order of G is n, is nothing but order of A. So this means order of the generator. We cannot say the generator, because once you have one generator, we are going to have a result which would tell what could be the other generators. So order of its generator A. Okay, now we have this remark: if the order of an element A in a group G is same as the order of the group, then G must be cyclic. See, what we proved in the previous result is whenever we have G generated by G is cyclic generated by A, G is generated by A, order of G is same as order of its generator. So here what we say is, if the order of an element A in G is same as order of the group, then G must be cyclic. Here cyclic given, and you are proving the orders to be the same. So here you have orders to be the same. It is actually this way you have established. Now we are going to see that even in this way it is true. So the reason for that, you take order of G to be n. Okay, order of G to be n, and A belonging to G to be of order n. So order of the group is same as order of an element A in G. Now we'll consider H to be a subgroup of G generated by A. So if I am able to show that H is G, then we are through. So by the above property, we must have order of H to be equal to order of A. Whenever G is generated by A, just now we proved that order of G is same as order of its generator. So here we have assumed that H to be generated by A. So by the above result, we must have order of H to be order of A. But order of A is assumed to be n. So order of H is n you have. So since order of H and order of G are the same, both of them are of the same order, and H is contained in G. H is a subgroup of G, so H is contained in G. Then we must have H to be equal to G. By the equality of sets, this is already discussed in one of the videos, that to prove that two sets are equal, you show that H is contained in A is contained in B, B is contained in A. If you want to show that A equals B, generally A must be contained in B, B must be contained in A. But if they happen to be finite sets, it is in it, you have one of them to be contained in the other one, and both of them are of the same order. So here to have H to be equal to G, both of them are of the same order and one is contained in the other. So we must have G to be H, but H is generated by A, so G must be generated. G must be generated by A. So whenever we have G to be, order of G to be equal to order of one of its elements, then we can say that G has to be cyclic. So we have this to be true in both ways. Whenever G is cyclic generated by A, order of G must be equal to order of its generator. And whenever order of G is, so whenever we have order of G is same as order of an element in G, then you must have G to be cyclic. It's an important property. Later when we prove any of the results based on cyclic, this is the technique that we'll be using. Next we are going to show that this property, if A is a generator of G, then so is its inverse. Its inverse will also be a generator. Now let G be generated by A. It's a cyclic group generated by A. You consider G to be in any element in G, then G can be written as some integral power of A, that is rewritten in this way. And you choose your, we never said that it should be positive integer. So we shall name this minus k to be, say, some m. So your G now is written as some integral power of A inverse. So thus G is an integral power of A inverse, showing that A inverse is also a generator of G. So that's a simple proof. Next, see, this one says that whenever A is a generator, A inverse is also a generator. The next one says that in an infinite cyclic group, we can have only A and A inverse to be only generators. You cannot have more than these two generators in an infinite cyclic group. Now, for the proof, we shall consider a G to be generated by A, and that is an infinite cyclic group. Now let B, so you have got one generator, you take B to be any other generator of G. Now as B belongs to G, A generates G, so we must have our B being written as some integral power of A. Now again, A belongs to G and B is any other generator you have considered. So B generates, so A can be written as some integral power of B. So this is what we have. So you consider A, that is nothing but B raised to M, but B is nothing but A raised to N, so you have this step. So you have this being rewritten as A raised to Nm. So this, when you multiply both sides by A inverse, you have A raised to Nm minus 1 to be identity element. So this means order of A is finite. So order of A is finite that you have, and order of A is less than or equal to Nm minus 1. But we have this to be an infinite cyclic group. So we cannot have this to happen unless otherwise Nm is 1. This forces us to conclude that Nm minus 1 equals 1. So Nm minus 1 equals 0. So that in turn implies Nm equals 1, and which in turn gives, because they are all integers, N and M are integers. So there is no other go, we'll have to have only this. So we have to have our generators for this infinite cyclic group to be just either A or A inverse. It is not just A or A inverse, these are the only generators. So next property is, if G is a finite cyclic group and order of G is n, then for every positive integer D which divides n, there exists a unique subgroup H of G of order D. Actually, this property helps us in determining the subgroups of a cyclic group. This property helps us in determining the subgroups of the given cyclic group. Given, of course, a finite cyclic group. Let G be a finite cyclic group of order n. Then for every positive divisor D of n, you can find a unique subgroup H of G. And what is the order of that subgroup? It will be D. Now let G be a finite cyclic group generated by A of order n. And let D divide n. So this is given to us. So because D divides n, we know that n can be written as some integer times D. Now we claim that order of A power m is D. Suppose order of A power m is S, then S is the least positive integer for which A power m is A power m raised to S is identity element. We shall name that as equation 1. Now A raised to n is E, that's because G is generated by A and that's of order n. Order of the generator is same as order of the cyclic group, so you have this step. But this n is rewritten as md, so you have this. Now that is again rewritten as A raised to m raised to d equal to E. This is named as equation 2. So from 1 and 2, what we conclude is this S is less than or equal to D. See, already you have this to be true and this also to be true. So we have you have assumed order of A power m to be s. So s is the least positive integer for A power m, and this d is any other integer. D is any other integer and s is the least positive integer, because we have assumed this to be the order. Order of an element is always the least positive integer. So you have the from 1 and 2, s must be less than or equal to d. Now we claim that this s is equal to d. We claim that this s is d. So suppose we assume that s to be less than d, then multiplying both sides by this positive integer m, we must have ms to be less than md, and md is taken as n, so m is less than n. So what you have is A power ms to be e with a number which is less than the least positive integer. So that cannot happen. That's a contradiction to the fact that you have n to be, or order of A to be n, or n is the least positive integer for which A power n is e. So our assumption is wrong, and therefore the other one holds, namely s is equal to d. So let h be the subgroup generated by A power m, then order of h is d. So we have got A power m raised to d to be e, that is one thing, and if we have s to be the order of A power m, and that s is nothing but d, also we have established. So we have our order of h to be d. So we have got a subgroup in G whose order is d. We have got a subgroup in G whose order is d. So now we have to show that this, so this proves the existence. Now we have to show the uniqueness part. Suppose K is any other subgroup of G, which is say generated by some A power K, because already we have established that any subgroup of G, which is a cyclic group, will be generated by A power some positive integer. So we shall assume that K to be any other subgroup of G generated by A raised to K with order of K, same order. Then what we need to prove is this, our H is same as K. Now having got this K and M, we are applying Euclidean algorithm to this K and M. So we can find integers R and Q such that K is MQ plus R with 0 less than or equal to R less than M. Now we claim that this R is 0. Suppose K is equal to MQ plus R with 0 less than R less than M. Then when we consider E, which is A power K raised to D, so you have this A power, this K is rewritten as MQ plus R, and this is what you have. And you are multiplying this, you are taking this inside, so you have this step. This must be MDQ. So you have this, but we know already that this is nothing but E. So you have A power RD to be E with RD less than MD. You have just R less than M only, but you are multiplying both sides by D. So you have this. So RD to be N, and again this is a contradiction to the fact that N is the least positive integer for which A power N is E. You have got a number which is less than n for which A power n is E. A power, that number is E. That's a contradiction. So we must have R to be 0. So when R is 0, you have K to be MQ. When R is 0, you have K to be MQ. So you have A power K to be A power M raised to Q. So this is nothing but a member of H. So you have your every element of K to be in H. Now both of them are of the same order, and one is contained in the other, and therefore they must be equal. So this proves the uniqueness. So we have shown that whenever G is a finite cyclic group and order of G is n and D is a divisor of n, then G must have a unique subgroup of order D. Whichever divisor that you have, then for that you can always find a subgroup with that order. Suppose I have considered 10. I have got a cyclic group whose order is say 10, and then 2 divides 10. So that says that this G must have a cyclic group of order 2. So remember, this result holds only if G is a finite cyclic group, not otherwise. Your G has to be finite cyclic group. And we can even say that later we are going to have Lagrange's theorem. So if we recall this property there, then we can conclude that converse of Lagrange's theorem is true in the case of finite cyclic group. Converse of Lagrange's theorem we are going to have later, and we can have converse of Lagrange's theorem to be true in the case of finite cyclic group. In the case of finite cyclic group. So we have proved the existence as well as the uniqueness. So this is what I already said. The number of distinct subgroups of a cyclic group is nothing but the number of divisors of n. So if you want to find a subgroup of a cyclic group, you find the divisors. So that will give. So how many other divisors that you have for that particular number, then you will have so many subgroups. Now the last property, if G is generated by A, that's a cyclic group of order n, then G is generated by, how can we find any other generator? If one generator is known, can we find the other generators of the cyclic group? So that question is answered by this property. It's also an important property to find all the generators of the given cyclic group if one is known. So how it could be done? This one says that whenever G is generated by A, G will also be generated by A raised to K. What is the relation between K and N? See, K is a number that we have introduced here. So there must be some relation between K and N. N is nothing but order of G. So A power K will also be a generator if one only if the GCD of K and N is 1. We must have the GCD of these two numbers to be 1. Then that is other than 1, there should not be any other common divisor. So it's a very important property. Now let G be generated by A and N is order of G. We shall take, see, it has got two things to be established. One is by assuming G to be generated by A power K, you have to show that K and N are relatively prime, and the other way around. Assuming this, you have to show that G is generated by A power K. So we shall assume first that G is generated by A power K. We claim that K and N are relatively prime. Now since A power K is also a generator of G and A belongs to G, we can write A as some integral power of this generator. So this gives A raised to KR minus 1 to be E. Right. Then we have A power N to be E, because order of G is assumed to be this and N is the least positive integer. And we know that whenever N is least and for some other integer you have this, then least must divide that any other integer. So based on that you have N dividing KR minus 1, and this in turn implies KR minus 1 as some integer times N, or KR minus Ln is equal to 1. You can just rewrite this as KR plus Qn as 1. So this by one of the results that in the preliminaries it has been mentioned that under integers this is mentioned. So if KR plus Qn is 1 means then GCD of K and N should be 1. So we have got whenever your G is generated by A power K, already G is generated by A whose order is N, the relation between K and N is K and N are relatively prime. Now for the converse part, we shall assume our GCD of k and n to be 1. Then there exists again by the same result. We can find integers q and r such that kr plus qn is 1. Now we consider a, which is a raised to, we are replacing 1 by this, so you have this, and a power n being e, you are just left with this. So your a is written as a power kr. So a is some integral power of a power k. Now we claim that g is generated by this. Any element a, when we consider, it's written as some integral power. So this is the generator that this is also a generator that we need to claim. So you consider x and g, then x can be written as, because g is generated by a, that's given. So you have to have x to be written as some integral power of a. So when we consider x, we have this a being written as a power kr, you have this step, and this again rewritten as a power k raised to lr. So your x's, which is an arbitrary element in G, is generated by a power k, because this x is written as some integral power of a power k. So G is generated by a power k. So whenever we have one generator of a given finite cyclic group with order say n, we can bring in the rest of the generators. And it also says that how many generators that we can have for this particular cyclic group of order n, how many generators that we can have. See, those numbers, a power k is a generator. Those numbers which are relatively prime to n is nothing but Euler's phi function. So you can have phi of n generators. How many generators you can have? Phi of n generators you can have for G generated by A of order n. So if one generator is known, you can bring out the other generators, and how many such generators that you can have, how many ever numbers which are less than n and relatively prime, but that number is nothing but Euler's phi function. So there will be phi of n generators for the given group G, which is cyclic of order n.